Welcome to the online lecture where we will discuss balancing chemical equations. Alright, so anytime we have a chemical reaction, we can represent it as a chemical equation. So whatever we're looking at in the test tube, whatever reaction's going on in front of us, we are able to represent it on paper, okay, with what's called a chemical equation. If we know exactly the substances we start with, we can figure out the substances that we'll end with as well. So if you remember, this is what a chemical equation looks like. It's a little off because the conversion between PowerPoint and this program isn't exactly right, but we get the idea. We've got reactants on the left, okay? So the substances on the left side, these are the things we start with in the chemical reaction. Those are the reactants. All right, and then we've got this reaction arrow, okay, which means a reaction has occurred, okay, between the reactants. So something new is being made is basically what that arrow is going to represent. And on the right side, we have the products. So here, this purple arrows should be for the products on the right side. And sometimes, not all the time, but sometimes in a chemical reaction, we can specify the states of matter that each of the products and reactants are in. And so we put that in parentheses behind each substance. So you'll see here this blue line is supposed to be pointing up to the, the little g in parentheses means gas. So in this case, we've got, and don't forget, anytime we've got these little numbers, they're going to be subscripts. So CH4 in the gas form plus oxygen in the gas form is going to react to form carbon dioxide in the gas form and H2O in the gas form. All right, so that is the representation of the burning of methane. All right, so anytime we write down a chemical equation, we need to make sure that matter is neither created nor destroyed, meaning that we keep in mind this law of conservation of matter, which says that whatever atoms you start with, those are the atoms that you have to end with, and you have to have equal numbers on both sides because matter cannot just disappear or reappear from nothing. So we must account for all the atoms on both sides of the equation. So if we take a look at this example in the picture, we've got 6 little hydrogen atoms, and we have 2 nitrogen atoms. So in the end, after they react, we still need to have 6 hydrogen atoms and 2 nitrogen atoms. All right, and so in fact over here we've got 6 hydrogen atoms, and here's our 2 nitrogen atoms. So in this case, this is a balanced chemical equation. If we had just put, H2 plus N2, okay, equals NH3, all right, we can even see from the very beginning that if we just left it like this, first off, we wouldn't have enough hydrogens to make NH3, and we would have one too many nitrogens because we start out with 2 and only end up with 1. Okay, so we can't, come up with more hydrogens or, just get rid of or disappear any nitrogens. So we always have to make sure that it's balanced. The only way for this equation to be balanced is to actually start with 3 molecules of hydrogen gas, okay, with 1 molecule of nitrogen gas, and in the end you're going to get 2 molecules of ammonia. Okay, so we got to balance the equation, and if you noticed, we didn't change any of these little subscript guys. Okay, they all stayed the same. All right, the only thing we changed, remember, is the coefficients. All right, the numbers out front. So here we put a 3 out front of the H2. The N just gets a 1. All right, remember 1s are invisible. We don't need to put them. And then the ammonia gets a coefficient of 2 so that we can balance everything out. So let's take a look and see how this works. All right, so this slide basically kind of summarizes what I was just explaining in the last one. To correct any problems where we write down the chemical formulas for the products and the reactants, and we somehow, like we saw, didn't have it in, excuse me, enough of one atom or if we had too many of another, we need to correct those problems by creating a balanced equation, okay, where the number of each type of atom is equal or the same on both sides. So like I said, we are only going to mess with those coefficients in front of the chemical formulas, okay, as needed. Coefficients change the number of molecules in the equation, but they don't change the kinds of molecules. That is super important to realize, okay? So up here in the picture, okay, we're working with H2 molecules. The 3 out front just means that there's 1, 2, 3 H2 molecules. It doesn't change the fact that they're H2 molecules. It just says there's 3 of them there. Okay, the same thing out here with the 2 in front of ammonia. All right, NH3 is the product, ammonia, but we are going to be making 2 of those molecules of ammonia. Okay, so it's not an N2H6 kind of compound. It's just 2 molecules of NH3. Okay, and probably the most important thing to remember is never, 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 never change those subscripts. Okay, never change the subscripts. If you change the subscripts, then you're changing the kind of molecule it is. Okay, so you never change the subscripts, just the outside coefficients. All right, so change coefficients only, never the subscripts, because we don't want to change the kind of molecules that are reacting. We just need to balance it to see how many molecules need to react with each other to make a certain product in the end. All right, so let's take a look at some examples on how to write balanced chemical equations. So for all of these, you're going to kind of need your knowledge of combining elements together to make compounds, writing those compound formulas out, and then balancing in the end. All right, so here's our example. It says, write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. All right, so don't freak out. Let's start with one compound at a time. Okay, so first thing it says, it's a reaction between solid silicon dioxide. Okay, so if we look on our periodic table, in fact, why don't you grab one, have one handy. Silicon dioxide it's using prefixes, so we know that it's got to be a covalent or molecular compound. So we have silicon, and then dioxide means O2. So silicon dioxide. Let me actually do that in white since the blue's not really showing up. There we go. Silicon dioxide, and it says solid, so we're going to put a little S behind it. So it's a reaction between silicon dioxide and solid carbon. Okay, so we're going to put a little plus sign, and we're going to put carbon. Carbon is not a polyatomic ion or anything like that, so he can stick by himself. Carbon, and we'll put a little S. All right, and then it says to produce. There's our arrow. Okay, because that means both of them are going to react together to make everything in the rest of the sentence. Solid silicon carbide. Okay, so let's take a look. We have silicon, all right, and carbon. All right, and we got to do solid. All right, and carbon monoxide gas. So let's go ahead and put carbon, and then monoxide means there's just one oxygen. And I'm kind of running out of room there, so we'll sneak the little gas symbol underneath. All right, so we go silicon dioxide solid plus carbon solid. It's going to react to form silicon carbide solid and carbon monoxide, gas. All right, so right now, if we take a look, we've got one silicon on both sides, so that's balanced. Here we've got 2 oxygen atoms on this side, but only 1 oxygen atom over here. Okay, so oxygen is unbalanced. So in order to balance that or make them equal, since we have 2 on the left and only 1 on the right, what we'll do is we will put a 2 out front of the carbon monoxide. That coefficient is always multiplied, okay, to each of the atoms in the molecule that it's in front of. So the 2 is going to mean that now that there is 2 oxygen atoms to balance out the left, okay, but there's also 2 carbon atoms as well. All right, so let's take a look. On the left side, we have 1 carbon atom. On the right side, we have 1 here, and now we have 2 there. So we have a total of 3 carbon atoms on the right-hand side. All right, so 3 on the right and 1 on the left, we have to put a 3 out front here in order to balance out the carbon atoms on both sides. Okay, so the coefficients here are going to be just a 1 in front of silicon dioxide, a 3 in front of the carbon on the left, and then on the right side, just a 1 for silicon carbide and a 2 in front of carbon dioxide gas. So balancing those using those coefficients to balance the atoms on both sides makes sure that we are using all of the atoms in our reactants and we're not coming up with anything new or just kind of making things disappear. All right, so the best way to get good at this is to practice, practice, practice. All right, the best way to make sure that you understand how to do this is to do lots and lots of practice problems. So we're going to do a couple more in these notes. Next practice problem says write a balanced equation for the combustion reaction between liquid octane and a component of gasoline and gaseous oxygen to form gaseous carbon dioxide and gaseous water. In fact, this is exactly what is the chemical reaction that goes on inside of your engine of your car. And, octane, found in gas, is going to be mixed with oxygen from the air inside of the little piston things, and there'll be a little spark that makes the reaction take, facilitates the reaction to get it going, takes place, and we get the formation of carbon dioxide and water. And that's basically the main component of your exhaust. So let's take a look and write a balanced equation for this. Okay, so we've got to first put down our first reactant that we come across, which is C8H18. Okay, and it says that's a liquid, so we're going to put that L behind it. Okay, and we're going to react that with gaseous oxygen. Remember, oxygen is Hofbrinkel. He's a diatomic gas, so he's not by himself. He's always written with a 2 down there with this subscript. All right, so he's in gaseous form, so we're going to put a G next to him. All right, and these two things are going to react to form gaseous carbon dioxide, okay, CO2 gas, and gaseous water, H2O, as a gas. All right, so now we have to take a look and do some balancing. All right, so if we take a look at carbon, we have, and one of the tricks, if you're still kind of shaky at this at first, is to kind of draw a line, right where that arrow is, and let's put our, make a list of all of the atoms that are on each side, and then just kind of take inventory on both sides. So on the left, we have 8 carbons. On the right, we have just 1 so far. On the left, we have 18 hydrogens, and on the right, we have 2. On the left, we have 2 oxygen, and on the right we have 2 from carbon dioxide plus 1 from water, so that's 3 total. All right, so let's take a look and see how we can balance these. Let's start on the top with carbon. Carbon is 8 on the left and 1 on the right. So what if we put an 8 out front here? Well, now we have to redo our math. Okay, so we have 8, now we have 8 carbon on the right, and we have 8 times 2, which is 16 oxygen on the right. All right, okay, so carbons are now balanced. Let's take a look at hydrogen. Hydrogen has 18 on the left, and right now we only have 2 hydrogens on the right. So in order to balance that out, well, 18 times what, 2 times what equals 18? Okay, that would be 9. So let's put a 9 out front here. So now we have, let's redo our math, we have 18 hydrogens, okay, on the right, which matches our 18 hydrogens on the left. But it also messes with our number of oxygens, okay. So now we've got 16 oxygens in the 8 molecules of carbon dioxide plus 9 more with the 9 that we put in front of H2O. So 16 plus 9 is 25. All right. So now we've got 2 on the left and 25 on the right. All right. Coefficients are always going to be whole numbers. So we're kind of stuck a little bit right now because 2 times what equals 25? Well, that would be 12 and a half, except we can't have a half a molecule. So when you're stuck like this and you've got everything else balanced, but you've got an odd number of one, type of atom on one side and an even number on the other side, what you do is you are going to just double everything, because that's how you make an odd number even, is to double it. Okay, so let's double our coefficients. Put a 2 right there. Okay, a 2 here. All right, and 8 times 2 is 16, so let's just put a 16 there. And 9 times 2 is 18, so let's change that to an 18, and let's redo our inventory. So on the left we have 2 times 8, which is 16 carbons. We have 2 times 18, which is 36 hydrogens. And now we have 2 times 2, which is 4 oxygens. Now on the right, we've got 16 carbons, so that still equals out. And we have, let's jump over to the hydrogens. We have 18 times 2, which is 36, which still balances out, which is good. And now let's take a look at those oxygens. We have 16 times 2, which is 32, plus 18. 32 plus 18 is 50. Okay, then we have 50 oxygens on the right, and we have 4 oxygens on the left. Okay, if we think about it, 50, or what times 2 equals 50? Well, that would be 25. All right, so if we change this from a 2 to a 25 out front, now we've got 50 oxygens on the left to balance out, and now we're good. Okay, so this one was kind of a doozy because we had to double the coefficients, but sometimes you have to do that when you're balancing equations. If you get everything balanced except one thing that's not balancing in the end because you've got an odd number on one side, well, to get rid of the odd number, just double it. Okay, so double the coefficient out front, but if you double one coefficient, you have to double all the coefficients. So that's exactly what we did. All right, let's do one more together, and you'll see that the last slide is a you try it slide. So let's do one more example together. It says, write a balanced equation for the reaction of solid aluminum. Okay, so we're going to have aluminum solid with aqueous sulfuric acid. Okay, and so remember, sulfuric acid, ic means it comes from the 8 version of the polyatomic ion. Okay, so sulfate is SO4. It has a -2 charge. So how many hydrogens do we need to balance out a -2 charge? That would be 2 hydrogens. So it's H2SO4, and that's aqueous, so we'll put the AQ. All right, and those two things are going to react to form aqueous aluminum sulfate. Okay, so we have AlSO4, but this is a metal-nonmetal combination. This is the first we've seen so far in these examples. Metal-nonmetal combination means we have to cancel charges by crisscrossing. So we got to think, okay, aluminum has a +3 charge, so that 3 is going to go on the outside down there by sulfate. We'll crisscross it. And sulfate has a -2 charge, so that 2 is going to come down by aluminum. So it's Al2SO4 in parentheses with a 3 on the outside. All right, and that was aqueous. And then we also get hydrogen gas. Remember, hydrogen is a diatomic gas. Remember Hofbrinkel, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine are all diatomic gases, which means that they're always found as a 2. Okay, so we got to put not just H, but H2. So there's a bunch of things you got to remember and keep in mind. All right, let's take a look at balancing this bad boy. Okay, so let's take inventory. We have aluminum on each side. We have hydrogen on each side. We have sulfur. Actually, I'm going to show you this trick of keeping the polyatomic ions together. Okay, so that you don't have to do the sulfurs and then the oxygens. You can always keep the polyatomic ions as long as they're kept together within the reaction. So you have like sulfate on the left and a sulfate on the right. Then you can keep them together when you're doing inventory. If they were broken up in any way, if, for example, we ended up on the right with SO3 instead of SO4, or just, S and the oxygens went to something else, then we couldn't do this. But since we have sulfate on both sides, we can keep them together. All right, so on the left side, we have 1 aluminum. On the right side, we have 2. On the left side, we have 2 hydrogens. On the right side, we have 2 hydrogens. On the left side, we have 1 sulfate group, but on the right side, we have 3 sulfate groups. Okay, because that 3 here. All right, so let's take a look at balancing them. So first off, we have 1 aluminum on the left and 2 on the right. So if we put a 2 out front here, we can change that to a 2 and balance the aluminums. Okay. Hydrogens are balanced for now. Let's take a look at sulfate. We have 2 on the, or I'm sorry, not 2, 3 on the right and only 1 on the left. So that means that we would have to put a 3 out front here, out front of the entire molecule that the sulfate is in. Okay, because remember, we can't change the subscripts. We can't shove little numbers in between the atoms. You have to put it out in front of the molecules. All right, so that gives us 3 sulfate, but we also changed the hydrogens as well. So now we have 3 times 2, which is 6. All right, so now we've got aluminum balanced, we have sulfates balanced, but we unbalanced hydrogen by adding the 3. So we have to go back and balance that guy. So we have 6 on the left, 2 on the right. Well, that's an easy fix because 2 times 3 is 6. So we put a 3 out front of the hydrogen gas, and now we've got a balanced equation. All right, and as promised, this is the last one that I want you guys to do on your own. Writing a balanced equation for solid iron with aqueous hydrochloric acid to form iron 3 chloride and hydrogen gas. So I do have the answer down there, but I want you to try it to make sure that you know how I got that answer. And if you have any questions about balancing equations, this again should be kind of a review. Hopefully it's kind of an easy review from high school chem. If you do have any questions though, please make sure you come see me so that we can get it straightened out, because in class we'll be talking about much more complicated things besides balancing equations. So this is kind of, this is some knowledge that you should have before you come to next class. All right, we'll see you then.